The night sky has always been a source of wonder, a canvas of twinkling lights that hints at the vastness of the cosmos. But what if I told you that what we see, those familiar stars and constellations, is barely the beginning? Beyond the visible lies a universe teeming with mysteries that defy explanation. Unexplained cosmic signals that seem to reach out across the void, celestial objects that behave in ways that challenge the very laws of physics, and phenomena so strange they leave even the brightest scientists scratching their heads. These aren't just curiosities, they're clues to the universe's deepest secrets. In this video, we'll uncover 32 of the most compelling pieces of evidence that reveal the uncharted and the extraordinary in our cosmos. From enigmatic signals to bizarre objects, each discovery pushes the boundaries of what we know and invites us to rethink our place in the grand tapestry of existence. So, are you ready to step beyond the familiar and explore the unknown? Let's dive in. In the summer of 1977, something extraordinary happened that would forever change how we think about the cosmos. A radio telescope at Ohio State University, known as the Big Ear, picked up a signal so unusual, so strikingly powerful, that the astronomer who discovered it scribbled, "Wow." In the margins of the data printout, this signal, lasting 72 seconds, was unlike anything we'd ever detected before. It came from the direction of the constellation Sagittarius, and its intensity was off the charts, so strong that it seemed to scream, "Pay attention." But here's the twist. After that brief burst, it vanished. No follow-up, no repeats, just silence. For decades, scientists have tried to explain the wow signal. Was it a message from an alien civilization finally reaching out across the void? Or was it a rare, natural cosmic phenomenon that we simply don't have the tools or knowledge to fully understand? What makes this signal so intriguing is that it fits the profile of what we'd expect from an intelligent source: narrowband, intense, and seemingly artificial. Yet, despite countless efforts to locate its origin, the wow signal remains one of the most tantalizing unsolved mysteries in astronomy. It's a reminder that even with all our advanced technology, the universe still holds secrets that defy explanation. This isn't just a story about a signal, it's a story about possibility. It challenges us to think bigger, to consider that we might not be alone in the universe, and to wonder what else might be out there waiting to be discovered. The wow signal isn't just a scientific curiosity, it's a beacon of hope, a cosmic nudge that says, "Keep looking." And as we continue to search the skies, who knows what other messages we might find. Fast radio bursts, or FRB, are like the universe's way of whispering secrets in a language we're still learning to decode. Imagine a signal so powerful that it releases more energy in a single millisecond than our sun does in an entire day. That's exactly what these mysterious bursts are: intense flashes of radio waves that streak across the cosmos, vanishing almost as quickly as they appear. First detected in 2007, FRBs have since become one of astronomy's most puzzling phenomena. They come from galaxies billions of light years away, yet their origins remain shrouded in mystery. Scientists have proposed a variety of explanations for what might be causing these fleeting bursts. Some think they could be the result of highly magnetized neutron stars, known as magnetars, releasing enormous amounts of energy in a cosmic tantrum. Others suggest collisions between dense objects like black holes or neutron stars could be the culprits. And then there's the more speculative idea: could these bursts be the work of advanced extraterrestrial civilizations, perhaps using them as a form of interstellar communication or even propulsion? While this theory is far from proven, it's a fascinating reminder of how much we still have to learn about the universe. What makes FRBs particularly challenging to study is their unpredictability. They don't follow a schedule or a pattern, they just happen, often without warning. This sporadic nature means that by the time we've detected one, it's already gone, leaving behind only a faint echo in our telescopes. But with each new detection, we gather more clues. For instance, some FRBs have been found to repeat, suggesting that whatever's causing them isn't a one-time event. This has opened up new avenues for research, allowing scientists to pinpoint their origins with greater precision. One of the most intriguing aspects of FRBs is what they reveal about the fabric of the universe itself. As these bursts travel across vast distances, they interact with the gas and dust between galaxies, leaving a kind of cosmic fingerprint. By studying these fingerprints, astronomers can map the otherwise invisible matter that fills the universe, giving us a clearer picture of its structure and composition. In a way, FRBs aren't just mysteries to be solved, they're also tools, helping us uncover the hidden details of the cosmos. So, what do these bursts tell us about the universe? At the very least, they remind us that space is far more dynamic and unpredictable than we often assume. They challenge us to rethink our understanding of cosmic events and to consider possibilities that might seem like science fiction until they're proven otherwise. Whether they're the result of natural phenomena or something more extraordinary, FRBs are a testament to the fact that the universe is still full of surprises, waiting for us to unravel them. And as we continue to listen to the whispers of these fleeting signals, who knows what other secrets they might reveal? Now, let's turn our attention to a star that has baffled scientists and stargazers alike, Tabby's star, also known as KIC 8462852. Located over 1,000 light-years away in the constellation Cygnus, this seemingly ordinary star has been anything but ordinary in its behavior. What sets Tabby's star apart is its bizarre and unpredictable dimming patterns. Unlike most stars, which dim in a regular, predictable rhythm due to orbiting planets or stellar activity, Tabby's star experiences sudden, dramatic drops in brightness, sometimes by as much as 22%. These dips are irregular, asymmetrical, and unlike anything we've ever observed before. When these unusual dimming events were first detected by NASA's Kepler Space Telescope in 2015, scientists scrambled to find an explanation. One early theory suggested that a massive swarm of comets or debris might be passing in front of the star, blocking its light. While this idea seemed plausible, it didn't quite account for the sheer scale and irregularity of the dimming. That's when another, more daring hypothesis emerged. Could an alien megastructure, like a Dyson sphere, be responsible? The idea of an advanced civilization constructing a massive array of solar panels or habitats around the star to harness its energy captured the public's imagination and sparked widespread speculation. Of course, the alien megastructure theory remains highly speculative, and most scientists lean toward more natural explanations. For instance, some suggest that the dimming could be caused by dust clouds or the remnants of a shattered planet or moon. Others propose that the star itself might be undergoing unusual internal processes, leading to its erratic behavior. But despite years of observation and analysis, no single explanation has fully solved the mystery of Tabby's star. What makes this star so fascinating is that it defies easy categorization. It's a cosmic puzzle that refuses to fit neatly into our existing models of stellar behavior. Beyond the mystery itself, Tabby's star serves as a powerful reminder of how much we still have to learn about the universe. It challenges us to question our assumptions and to remain open to possibilities we might not yet understand. Whether the answer lies in natural phenomena or something more extraordinary, this star has become a symbol of the enduring enigmas that await us in the cosmos. As we continue to study Tabby's star, each new observation brings us closer to unraveling its secrets. With advanced telescopes and innovative techniques, astronomers are refining their models and gathering more data to piece together the puzzle. What's clear is that this star isn't just a curiosity, it's a gateway to deeper questions about the nature of stars, the potential for intelligent life, and the countless mysteries that still lie hidden in the vast expanse of space. And as we peer into the depths of the universe, stars like Tabby's remind us that even the familiar can hold profound surprises, urging us to keep exploring, keep questioning, and keep wondering. In the vast expanse of the universe, there's an invisible force shaping everything we see: stars, galaxies, even the very fabric of space itself. Yet, for all its influence, it remains completely hidden from our eyes and instruments. This mysterious entity is known as dark matter, and it's one of the most profound puzzles in modern science. Despite making up roughly 27% of the universe, dark matter doesn't emit, absorb, or reflect light, making it impossible to observe directly. So how do we even know it exists? The answer lies in its gravitational effects. When astronomers study the motion of galaxies and the way they cluster together, they notice something strange. The visible matter, stars, gas, and dust simply doesn't account for the gravitational forces at play. Galaxies spin faster than they should, and their outer regions move as if they're being pulled by something unseen. This discrepancy led scientists to propose the existence of dark matter, a form of matter that interacts with gravity but remains invisible to all other forms of detection. It's like hearing footsteps in an empty room. You can't see the source, but you know something is there. The hunt for dark matter has taken scientists down a labyrinth of possibilities. One leading theory suggests it's made up of exotic particles that don't interact with light or ordinary matter. These hypothetical particles, often referred to as WIMP, weakly interacting massive particles, could be the key to unlocking this cosmic riddle. Experiments deep underground, shielded from cosmic rays, have been searching for these elusive particles for decades, yet so far they've come up empty-handed. This has led some to wonder if dark matter might be something even more bizarre, perhaps a relic from the early universe or a manifestation of extra dimensions we can't yet perceive. But what if dark matter isn't a particle at all? Some scientists have proposed an even more radical idea. What if our understanding of gravity is incomplete? This alternative theory, known as modified Newtonian dynamics or MUND, suggests that the effects we attribute to dark matter might instead stem from a flaw in our current laws of physics. While this idea is controversial, it highlights just how little we truly understand about the forces that govern the cosmos. The implications of solving the dark matter mystery are staggering. If we can uncover its true nature, it could reshape our understanding of the universe's structure, its origins, and even its ultimate fate. It could also open doors to entirely new realms of physics, revealing insights into the fundamental nature of reality. For now, dark matter remains a cosmic ghost, a shadowy presence that both frustrates and inspires us. It's a reminder that even in the most familiar corners of the universe, there are still secrets waiting to be uncovered. And as we continue to probe the depths of space, who knows what other hidden forces might be lurking just beyond our reach? While dark matter hides in the shadows, shaping the cosmos through its gravitational pull, there's another, even more enigmatic force at work, one that's not pulling the universe together but pushing it apart. This mysterious force is known as dark energy, and it's responsible for one of the most startling discoveries in modern cosmology: the accelerated expansion of the universe. Imagine the universe as a balloon being inflated faster and faster over time, with galaxies racing away from each other at ever-increasing speeds. That's the effect of dark energy, a force so powerful that it makes up roughly 68% of the universe's total energy content. Yet, despite its overwhelming presence, we know almost nothing about what it actually is. Unlike dark matter, which clumps together and interacts with gravity, dark energy is thought to be spread evenly throughout space. It doesn't gather in galaxies or clusters. Instead, it's woven into the very fabric of the cosmos, acting as a kind of anti-gravity that counteracts the pull of matter. The discovery of dark energy came as a shock to scientists in the late 1990s when observations of distant supernova revealed that the universe's expansion wasn't slowing down as expected but speeding up. This revelation turned our understanding of cosmology on its head, raising profound questions about the nature of space and time. So, what could dark energy be? One leading idea is that it's an intrinsic property of space itself, a concept known as the cosmological constant, first proposed by Albert Einstein over a century ago. In this view, empty space isn't truly empty. It contains a kind of energy that drives expansion. But here's the catch: the amount of energy predicted by this theory is vastly different from what we observe, creating a puzzle that scientists are still struggling to solve. Another possibility is that dark energy arises from a new, undiscovered field that permeates the universe, similar to the Higgs field but with very different effects. This field could fluctuate over time, potentially explaining why dark energy's influence seems to vary across cosmic history. The implications of dark energy go far beyond mere curiosity. Understanding this force is key to predicting the ultimate fate of the universe. If dark energy continues to dominate, the cosmos could face a big freeze, where galaxies grow so distant from one another that the universe becomes cold, dark, and empty. Alternatively, if dark energy intensifies over time, it could lead to a big rip, tearing apart galaxies, stars, and even atoms themselves. These scenarios may sound like science fiction, but they're grounded in real scientific theories, highlighting just how much is at stake in unraveling the mystery of dark energy. What makes dark energy so fascinating and so frustrating is that it's both everywhere and nowhere. It's everywhere in the sense that it fills the universe, driving its expansion. Yet, it's nowhere in the sense that we can't detect it directly. We only infer its existence through its effects on the cosmos, like a cosmic puppeteer pulling strings we can't see. This duality makes dark energy one of the greatest challenges in modern physics, a puzzle that demands new ideas, new tools, and perhaps even a new understanding of the fundamental laws of nature. As we grapple with the mystery of dark energy, we're reminded of how much we still have to learn about the universe. It's a humbling thought, but also an inspiring one. Every unanswered question is an invitation to explore, to question, and to push the boundaries of what we know. Whether dark energy is a property of space, a new kind of field, or something entirely beyond our current understanding, its discovery has already transformed our view of the cosmos. And as we continue to probe its secrets, who knows what other surprises the universe might have in store? Deep within the cosmic tapestry, hidden behind the dense veil of stars and dust in our Milky Way, lies a mystery so powerful that it's tugging entire galaxies toward it, including our own. This enigmatic force is known as the Great Attractor, and it's one of the most perplexing gravitational anomalies ever discovered. Imagine a cosmic magnet, invisible yet irresistible, drawing galaxies across the universe into its grasp. For decades, scientists have been trying to unravel its secrets, but its location directly behind the galactic plane makes it nearly impossible to observe directly. What could be generating such an immense gravitational pull, and why does it remain so elusive? The story of the Great Attractor begins with a curious observation. Galaxies in our local universe, including the Milky Way, are all moving in the same direction at astonishing speeds. This motion isn't random. It's as if something colossal is pulling them along. At first, astronomers thought this motion might be explained by the Virgo cluster, a massive grouping of galaxies relatively close to us. But as they mapped the velocities of galaxies more precisely, they realized that the Virgo cluster alone couldn't account for the sheer magnitude of this movement. There had to be something even more massive, something hidden from view, exerting its influence. The Great Attractor lies about 250 million light-years away, in the direction of the constellation Centaurus. But here's the catch: it's obscured by the Milky Way's galactic plane, a region so packed with stars, gas, and dust that it blocks our view of what lies beyond. It's like trying to peer through a dense fog. You know something is there, but you can't quite make it out. To complicate matters further, the Great Attractor isn't just a single object. It's part of a much larger structure known as the Laniakea supercluster, a vast network of galaxies spanning over 500 million light-years. Within this supercluster, the Great Attractor acts as a gravitational focal point, drawing galaxies toward it like water spiraling down a cosmic drain. So, what could the Great Attractor be? One leading theory suggests it's a massive cluster of galaxies, possibly containing trillions of stars, bound together by their collective gravity. If this is the case, it would be one of the most massive structures in the observable universe. However, even this explanation doesn't fully account for the extraordinary gravitational pull we're observing. Some scientists have speculated that there might be something even more extraordinary at play, perhaps an unseen concentration of dark matter, or even a supermassive black hole on a scale we've never encountered before. Others have proposed that the Great Attractor could be part of an even larger cosmic structure, hinting at a web of interconnected superclusters that we're only beginning to map. The Great Attractor isn't just a scientific curiosity, it's a challenge to our understanding of the universe's structure and evolution. It forces us to confront the limits of our knowledge and the tools we use to explore the cosmos. While advancements in infrared and radio astronomy have allowed us to peer through the galactic planes obscuring dust, much about the Great Attractor remains shrouded in mystery. Each discovery brings us closer to understanding this gravitational enigma, but it also raises new questions, reminding us just how much we still have to learn. What makes the Great Attractor so fascinating is that it's not just a distant anomaly, it's a force that's shaping our own galaxy's destiny. Over billions of years, the Milky Way and its neighbors will continue their journey toward this mysterious gravitational hub, pulled by a force we can't yet fully comprehend. It's a humbling reminder that even as we explore the vastness of space, we're still part of a much larger cosmic dance, orchestrated by forces beyond our current understanding. The Great Attractor isn't just a destination, it's a symbol of the universe's endless mysteries, urging us to keep looking, keep questioning, and keep exploring. In October 2017, astronomers made a discovery that sent ripples through the scientific community: a visitor from another star system. Named Oumuamua, which means scout or messenger in Hawaiian, this mysterious object became the first confirmed interstellar traveler to pass through our solar system. Unlike anything we'd ever seen before, Oumuamua wasn't just a fleeting curiosity. It was a cosmic enigma that challenged our understanding of the universe. What made Oumuamua so extraordinary was its peculiar shape and behavior. Most asteroids and comets in our solar system are roughly spherical or lumpy, but Oumuamua was different. It was elongated, stretching up to 800 meters in length but only about 80 meters wide. Imagine a cosmic cigar tumbling through space, its surface dark and reddish, reflecting very little light. But the mystery didn't end there. As Oumuamua sped away from the sun, it did something unexpected. It accelerated. This wasn't the kind of acceleration you'd expect from gravity alone. It was as if something else was pushing it, adding fuel to the fire of speculation. Naturally, this unusual behavior led to a flurry of theories. Some scientists proposed that Oumuamua might be a comet, venting gases that acted like a natural thruster, causing its acceleration. However, no visible tail or coma. the cloud of gas and dust that typically surrounds comets was detected. Others suggested it could be a fragment of a shattered planet or a piece of debris ejected from a distant star system. But the most tantalizing idea came from those who wondered if Oumuamua might be something far more extraordinary, an artificial object, perhaps even a probe sent by an advanced extraterrestrial civilization. This theory, while speculative, captured the public's imagination and sparked intense debate among scientists. The idea of an alien probe isn't as far-fetched as it might sound. In the vastness of space, it's not impossible that a civilization could send objects to explore other star systems, much like we've sent spacecraft like Voyager and New Horizons into the cosmos. Oumuamua's unusual shape and acceleration seem to fit the profile of something designed rather than something naturally occurring. But without more data, this theory remains just that, a theory. What's undeniable is that Oumuamua's brief visit left us with more questions than answers. Where did it come from? What is it made of? And most importantly, what can it teach us about the universe beyond our solar system? These questions have spurred a renewed interest in interstellar objects, leading to the development of new tools and missions designed to detect and study similar visitors in the future. Projects like the Vera-C, Rubin Observatory and the European Space Agency's Comet Interceptor aim to give us a closer look at these cosmic travelers, potentially unlocking secrets we've yet to imagine. Oumuamua's story is a reminder that the universe is full of surprises. It's not just a collection of stars and planets. It's a dynamic, ever-changing expanse filled with objects and phenomena that defy our expectations. Whether Oumuamua was a natural oddity or something more, its journey through our solar system has left an indelible mark on our understanding of the cosmos. It's a testament to the fact that even the smallest, most fleeting visitors can challenge our assumptions and inspire us to look beyond the familiar into the vast unknown. And as we continue to explore, who knows what other interstellar messengers might be waiting to reveal their secrets. While the universe teems with billions of stars and trillions of planets, one question looms larger than any other: where is everybody? This is the essence of the Fermi Paradox, a profound and puzzling question that challenges our understanding of the cosmos. Named after physicist Enrico Fermi, who famously posed it during a casual conversation in 1950, the paradox asks why, in a universe so vast and ancient, we haven't encountered any signs of intelligent extraterrestrial life. With countless stars and planets, many of which are Earth-like and potentially habitable, the sheer probability suggests that life should be abundant. Yet, as far as we can tell, the universe is silent. So, what's going on? One way to think about the Fermi Paradox is to consider the numbers. Our galaxy alone contains over 200 billion stars, and many of these stars host planets within their habitable zones, regions where conditions might allow liquid water and therefore life to exist. When you factor in the billions of other galaxies in the observable universe, the odds seem overwhelmingly in favor of life arising somewhere, perhaps even thriving. And yet, despite decades of searching, we've found no definitive evidence of intelligent civilizations. No signals, no artifacts, no signs of advanced technology. It's as if the universe is a vast, empty stage and we're the only actors. This silence has led scientists to propose a variety of explanations, each more thought-provoking than the last. One possibility is that intelligent life is incredibly rare, so rare that even in a universe this big, we might be among the first or only civilizations to emerge. This idea, known as the rare Earth hypothesis, suggests that the conditions necessary for complex life are so specific and unlikely that Earth might be a cosmic fluke. Another theory posits that intelligent civilizations inevitably self-destruct before they can develop the technology to communicate across interstellar distances. Whether through war, environmental collapse, or some other catastrophe, this great filter could explain why we haven't found anyone else out there. But what if the problem isn't with the universe, it's with us? Some scientists argue that our methods of searching for extraterrestrial life might be too limited. After all, we're looking for signals and signs that we would recognize based on our own understanding of technology and communication. What if advanced civilizations use methods we can't even conceive of? Or what if they're deliberately hiding, either out of caution or disinterest in contacting less advanced species like us? These ideas push us to rethink not just how we search for life, but also what we're searching for. The Fermi Paradox isn't just a scientific puzzle, it's a philosophical one. It forces us to confront our assumptions about life, intelligence, and our place in the cosmos. Are we truly alone, or are we simply looking in the wrong way? Could it be that the universe is teeming with life, but it's so different from ours that we can't recognize it? Or is there some universal truth about the fragility of civilizations that we've yet to grasp? These questions don't just challenge our knowledge, they challenge our imagination. What makes the Fermi Paradox so compelling is that it doesn't just ask whether we're alone, it asks what it means to be alone. It invites us to consider the possibility that we might be unique, not just in our galaxy, but in the entire universe. It's a humbling thought, but also an inspiring one. If we are alone, then the responsibility to explore, to understand, and to preserve life falls entirely on us. And if we're not alone, then the universe is far stranger and more wondrous than we've ever imagined. Either way, the Fermi Paradox reminds us that the search for answers is as important as the answers themselves. So, as we continue to gaze at the stars and listen for signals, let's remember, the silence isn't just a mystery, it's an invitation to keep searching, keep wondering, and keep dreaming. High above our planet, orbiting silently in the vast expanse of space, lies a mystery that has captured imaginations for decades: the Black Knight satellite. First mentioned in the 1950s, this enigmatic object has been the subject of countless theories, ranging from the scientifically plausible to the wildly speculative. Some claim it's an ancient alien artifact, a piece of extraterrestrial technology sent to observe humanity. Others argue it's nothing more than space debris or a case of misinterpreted data. But regardless of its true nature, the Black Knight has become a symbol of our enduring fascination with the unknown, a cosmic riddle that refuses to be solved. The story of the Black Knight begins with strange radio signals detected by Nikola Tesla in the late 19th century. Tesla, a pioneer in electrical engineering, believed these signals might be evidence of intelligent life attempting to communicate with Earth. Decades later, in the 1950s, reports surfaced of an unidentified object orbiting Earth, captured by both military radar and civilian observers. The object appeared to be artificial, leading to speculation that it could be a satellite long before humanity had launched its own. This sparked the idea of the Black Knight, a mysterious visitor from beyond our world. Over the years, the Black Knight has been linked to various sightings and anomalies. In 1998, during a space shuttle mission, astronauts captured images of what appeared to be a dark, irregularly shaped object floating in orbit. While NASA later identified it as a thermal blanket lost during a previous mission, the image reignited interest in the Black Knight myth. Similarly, satellite trackers have occasionally detected unusual objects in orbit, only to later determine they were pieces of debris or defunct satellites. Yet, despite these explanations, the legend persists, fueled by a mix of curiosity, skepticism, and the human desire to believe in something greater. So, could the Black Knight be an alien satellite? The idea isn't entirely without merit. If an advanced civilization had visited Earth in the distant past, it's possible they left behind a probe or device to monitor our progress. Such an object could remain functional for millennia, silently observing from above. Alternatively, the black night might represent a natural phenomenon or a piece of space junk that's been misinterpreted over time. The truth is, without concrete evidence, we're left to speculate, and that's where the magic of the black night lies. What makes the black night so compelling isn't just the possibility of its extraterrestrial origin, but what it represents about us. It's a reflection of our curiosity, our longing to connect with the cosmos, and our willingness to entertain the idea that we're not alone. Whether it's a relic of an ancient civilization, a piece of modern debris, or simply a story we've told ourselves, the black night reminds us that the universe is full of mysteries waiting to be explored. And as we continue to search the skies, who knows what other enigmatic objects might be watching us from the shadows of space? Imagine a place so vast and empty that it could swallow entire galaxies without a trace. This isn't science fiction, it's the Boötes void, a cosmic anomaly that stretches across an astonishing 330 million light-years. To put that into perspective, if you were to travel at the speed of light, it would take you more than 300 million years to cross this desolate expanse. And yet, despite its immense size, the Boötes void is eerily barren, containing far fewer galaxies than any other region of its scale. It's not just a gap in the universe, it's a gap in our understanding of how the cosmos is structured. Discovered in the 1980s, the Boötes void immediately stood out as something extraordinary. Most regions of space, even the emptiest ones, are dotted with galaxies, forming a kind of cosmic web that fills the universe. But the Boötes void is different. It's like a blank canvas in a gallery full of paintings. Astronomers estimate that it contains only around 60 galaxies, a fraction of what you'd expect in an area that large. To give you a sense of scale, a typical region of space that size would host tens of thousands of galaxies. So, what's going on here? How did this void come to be, and what does it tell us about the universe? One possibility is that the Boötes void is the result of a cosmic accident, a fluke of the universe's expansion. During the early moments of the Big Bang, fluctuations in density could have created regions of extreme emptiness like bubbles in a cosmic foam. Over billions of years, these regions expanded, leaving behind vast voids like the one in Boötes. But even this explanation doesn't fully account for the sheer scale of this emptiness. Some scientists have proposed that the void might be the result of something more profound, perhaps an interaction with dark energy or even the influence of a parallel universe. While these ideas are speculative, they highlight just how little we understand about the forces that shape the cosmos. The Boötes void isn't just a curiosity. It's a challenge to our assumptions about the universe. We tend to think of space as uniform, filled with galaxies and stars in more or less equal measure. But the Boötes void reminds us that the universe is far from uniform. It's a patchwork of dense clusters and vast emptiness, a tapestry woven with threads of light and shadow. This raises a fascinating question. If there are regions so empty, what else might be hiding in the gaps? Could there be structures or phenomena we haven't yet imagined lurking in the darkness? For astronomers, the Boötes void is both a puzzle and an opportunity. Its emptiness makes it a unique laboratory for studying the universe's structure and evolution. By mapping the few galaxies within the void, scientists can learn more about how galaxies form and interact in such extreme environments. It also offers a chance to study the effects of dark energy, which may play a role in shaping these vast empty regions. In a way, the Boötes void is a window into the unknown, a place where the rules we think we know about the universe might not apply. What's perhaps most striking about the Boötes void is what it represents, the idea that even in a universe as vast and seemingly predictable as ours, there are still mysteries that defy explanation. It's a reminder that for all we've learned about the cosmos, there's so much more we don't understand. Whether the Boötes void is the result of natural processes or something more extraordinary, it challenges us to think bigger, to question our assumptions, and to keep exploring the unknown. And as we peer into the depths of space, who knows what other voids or wonders might be waiting to be discovered? As we journey deeper into the mysteries of the cosmos, we come across an anomaly that once left scientists scratching their heads, a subtle but persistent puzzle known as the Pioneer Anomaly. Back in the 1970s and 80s, two spacecraft, Pioneer 10 and Pioneer 11, embarked on bold missions to explore the outer reaches of our solar system. These pioneers, aptly named for their trailblazing roles, sent back invaluable data about Jupiter, Saturn, and the vast expanse beyond. But as they ventured farther from Earth, something strange began to happen. Both spacecraft experienced an unexpected and unexplained deceleration, as if an invisible hand were gently tugging them back toward the Sun. This mysterious effect, dubbed the Pioneer Anomaly, became one of the most perplexing enigmas in the history of space exploration. At first, the anomaly was so slight that it could have been dismissed as a measurement error. But as the years went by and the data piled up, it became clear that this was no glitch. The spacecraft were slowing down more than they should have been, deviating from the precise trajectories predicted by Newton's laws of motion and Einstein's theory of general relativity. For decades, scientists proposed a wide range of explanations, from the mundane to the extraordinary. Could it be the gravitational pull of unseen dark matter? Or perhaps a flaw in our understanding of gravity itself? Some even speculated that the anomaly might be evidence of new physics, hinting at forces or phenomena we've yet to discover. The leading explanation today points to something far less dramatic but no less fascinating: thermal radiation. As the spacecraft traveled through the cold depths of space, the heat generated by their onboard systems and radioactive power sources was emitted unevenly. This uneven radiation, it turns out, acted like a tiny but constant push, slowing the spacecraft ever so slightly over time. While this explanation has gained widespread acceptance, it took years of meticulous analysis and modeling to confirm. The Pioneer Anomaly serves as a powerful reminder that even the most well-understood systems can hold surprises, especially when operating in the unforgiving environment of space. What makes the Pioneer Anomaly so compelling isn't just the mystery itself, but what it teaches us about the process of scientific discovery. It's a story of curiosity, persistence, and the willingness to question even the most fundamental assumptions. For years, this tiny discrepancy challenged our understanding of the laws that govern the universe, prompting scientists to rethink and refine their models. And while the answer may ultimately lie in the realm of engineering rather than groundbreaking physics, the journey to uncover it has deepened our appreciation for the complexities of space exploration. The Pioneer Anomaly also underscores the importance of precision in science. The deviation observed in the spacecraft's trajectories was minuscule, less than a billionth of the acceleration we experience due to Earth's gravity. Yet, detecting and explaining such a tiny effect required an extraordinary level of ingenuity and collaboration. It's a testament to the meticulous nature of scientific inquiry and the lengths we'll go to understand even the smallest details of the cosmos. As we reflect on the Pioneer Anomaly, it's worth considering how many other mysteries might be hiding in plain sight, waiting for the right tools, the right perspective, or the right moment to reveal themselves. Space is full of surprises, and each one, whether a subtle deceleration or a dramatic cosmic event, offers a chance to learn something new. The Pioneer Anomaly may no longer be a mystery, but its legacy lives on, reminding us that exploration is as much about the questions we ask as the answers we find. And as we continue to push the boundaries of our knowledge, who knows what other anomalies might be waiting to challenge us next, beyond the orbit of Neptune, where the sun's light grows faint and the icy remnants of our solar system's formation drift in the cold, lies a region known as the Kuiper Belt. This vast expanse, home to countless icy bodies and dwarf planets like Pluto, is a treasure trove of clues about our solar system's early history. But as we venture farther out, something strange happens, a sudden, dramatic drop in the number of objects, as if the Kuiper Belt has hit a cosmic wall. This mysterious boundary is called the Kuiper Cliff, and it's one of the most puzzling features in our solar system's outer reaches. The Kuiper Cliff isn't just a minor curiosity, it's a stark deviation from what we'd expect to see. Normally, as you move outward through the Kuiper Belt, the number of objects should gradually decrease, thinning out as you approach the edge. But instead, astronomers have observed a sharp, almost abrupt cutoff, a cliff where the population of icy bodies plummets. This unexpected boundary raises a host of questions. Why does the Kuiper Belt end so suddenly? What could be causing this dramatic drop? And could there be something lurking beyond the cliff, influencing the distribution of these objects? One of the leading theories is that the Kuiper Cliff might be evidence of an unseen planet, a hidden world far beyond the known reaches of our solar system. This hypothetical planet, often referred to as Planet 9, could be several times more massive than Earth, orbiting the Sun at an extreme distance. Its gravitational pull might be sculpting the Kuiper Belt, sweeping away objects near the cliff and creating the sharp boundary we observe. While this idea is still speculative, it's supported by computer simulations that show how a distant planet could produce exactly this kind of effect. But if Planet 9 exists, why haven't we found it yet? The answer lies in its distance and darkness. A planet that far out would reflect almost no sunlight, making it incredibly difficult to detect with current telescopes. Another possibility is that the Kuiper Cliff could be the result of interactions with passing stars. Over billions of years, our solar system has likely encountered other stars that came close enough to disrupt the outer regions of the Kuiper Belt. These gravitational encounters could have stripped away objects near the edge, leaving behind the sharp drop-off we see today. While this theory is plausible, it's hard to prove as it relies on events that happened long ago and left little trace. What makes the Kuiper Cliff so fascinating is that it's not just a boundary, it's a clue. It hints at forces and phenomena we don't yet fully understand, challenging our assumptions about the solar system's structure and evolution. Whether the answer lies in a hidden planet, ancient stellar encounters, or something entirely unexpected, the Kuiper Cliff reminds us that even the familiar regions of our cosmic neighborhood still hold secrets waiting to be uncovered. As astronomers continue to study this enigmatic boundary, new missions and advanced telescopes promise to shed light on its mysteries, projects like the Vera C. Rubin Observatory, with its unparalleled ability to survey the sky, could help us detect faint objects at the edge of the Kuiper Belt, or even uncover the elusive Planet 9. Each discovery brings us closer to understanding not just the Kuiper Cliff, but the broader story of how our solar system formed and evolved. The Kuiper Cliff is more than just a scientific puzzle. It's a reminder that the universe is full of surprises, even in our own backyard. It challenges us to keep exploring, to keep questioning, and to remain open to the possibility that there's always more to learn. Whether it's a hidden planet, a relic of ancient stellar encounters, or something beyond our current imagination, the Kuiper Cliff invites us to peer into the unknown and to wonder what other secrets might be waiting just beyond the edge of what we know. The cosmic microwave background, or CMB, is often described as the universe's oldest photograph, a snapshot of the cosmos just 380,000 years after the Big Bang. This faint afterglow, a sea of microwaves stretching across the entire sky, tells the story of the universe's infancy. But within this ancient tapestry, there's a peculiar anomaly that has puzzled scientists for years, a region so unusually cold that it stands out like a cosmic bruise. Known as the cold spot, this enigmatic feature isn't just a curiosity. It's a profound challenge to our understanding of the universe's origins and perhaps its very structure. The cold spot, first detected by NASA's Wilkinson Microwave Anisotropy probe in 2004, is a region of the CMB that's significantly colder than its surroundings. To put it in perspective, while most of the CMB varies by only tiny fractions of a degree, the cold spot is about 70 microkelvin colder than the average. That might not sound like much, but in the context of the universe's earliest moments, it's a glaring discrepancy. What makes this even more intriguing is the cold spot size. It spans nearly 1 billion light-years, making it one of the largest structures ever observed in the cosmos. So, what could cause such a vast and frigid anomaly? One leading theory suggests that the cold spot might be the imprint of a cosmic void, a region of space that's unusually empty, even by the standards of the universe. Voids are naturally colder because there's less matter to absorb and re-emit energy, and their gravitational pull can create a kind of cold shadow in the CMB. If the cold spot is indeed a void, it would be one of the largest ever discovered, stretching the limits of what we thought possible for such structures. But even this explanation doesn't fully account for the cold spot's extreme temperature. Some scientists have proposed that the void might be interacting with dark energy in ways we don't yet understand, amplifying its cooling effect. Then there's the more speculative idea, one that sounds like it belongs in a science fiction novel but is grounded in serious physics. Could the cold spot be evidence of a collision with another universe? According to some theories in multiverse cosmology, our universe might not be alone. Instead, it could be part of a vast multiverse where countless other universes exist alongside our own. If one of these neighboring universes collided with ours in the distant past, it might have left behind a kind of cosmic scar, a region of space that's colder and less dense than the rest. While this idea is still highly theoretical, it's a tantalizing possibility that could reshape our understanding of reality itself. What makes the cold spot so fascinating is that it doesn't just challenge our understanding of the early universe, it challenges our understanding of the universe as a whole. Is it a natural phenomenon, a product of the universe's chaotic beginnings, or is it a sign of something far more extraordinary, a glimpse into a reality beyond our own? These questions aren't just academic, they're deeply existential, forcing us to confront the limits of our knowledge and the mysteries that lie beyond. As astronomers continue to study the cold spot, new observations and simulations are helping to narrow down the possibilities. Projects like the European Space Agency's Planck satellite have provided more detailed maps of the CMB, offering fresh insights into this cosmic anomaly. Yet, despite these advances, the cold spot remains an open question, a reminder that even the most fundamental aspects of the universe are still shrouded in mystery. It's a humbling thought, but also an inspiring one, a testament to the fact that the cosmos is still full of surprises, waiting for us to uncover them. The cold spot isn't just a scientific puzzle. It's a window into the unknown, a place where the rules we think we know about the universe might not apply. Whether it's the footprint of a cosmic void or the echo of a parallel universe, it invites us to think bigger, to question our assumptions, and to keep exploring the vast, uncharted frontiers of space. And as we peer deeper into the mysteries of the CMB, who knows what other anomalies or revelations might be waiting to be discovered? As we continue to unravel the mysteries of the cosmos, we encounter a fundamental question that strikes at the heart of our understanding of the universe. Where is all the ordinary matter? You might think that with all our advanced telescopes and instruments, we'd have a pretty good handle on the stuff that makes up stars, planets, and even us. But here's the surprising truth: half of it is missing. This is the missing Baryon problem, a cosmic puzzle that has left scientists scratching their heads for decades. Baryons, the protons and neutrons that form the building blocks of ordinary matter, are supposed to be everywhere. Yet, when we tally up all the visible matter in the universe, we come up short. So, where is it hiding? To understand the scale of this mystery, let's start with what we know. Ordinary matter, the kind we can see and touch, makes up only about 5% of the universe's total mass and energy. The rest is dominated by dark matter and dark energy, those elusive forces that shape the cosmos in ways we're still trying to comprehend. Even within that small fraction of ordinary matter, though, there's a glaring discrepancy. Based on the universe's early history, as revealed by the cosmic microwave background, we know how much baryonic matter should exist, but when we look around, we can only account for about half of it. That's a lot of missing material, enough to fill entire galaxies. So, what's going on? Recent breakthroughs have brought us closer to solving this cosmic whodunit. Scientists now believe that the missing baryons might be hiding in a vast, diffuse network of gas that fills the space between galaxies. This gas, known as the warm-hot intergalactic medium, or WIM, is incredibly hard to detect. It's not dense enough to form stars or emit much light, and it's so hot that it glows faintly in X-rays rather than visible light. But despite its elusiveness, the WIM could be the key to finding the universe's missing matter. Observations from space telescopes like Chandra and XMM Newton have begun to reveal faint traces of this gas, offering tantalizing clues to its distribution and properties. But even with these discoveries, the mystery isn't fully solved. The WIM is incredibly difficult to study, and mapping its structure across the vastness of space is no small feat. Some scientists have turned to innovative techniques, like using the light from distant quasars' extremely bright galactic cores, to probe the gas. As this light passes through the WIM, it leaves behind a kind of cosmic fingerprint, revealing the presence and properties of the gas. These observations suggest that the WIM could indeed account for the missing baryons, but there's still much we don't know about its exact composition and distribution. The missing baryon problem isn't just a scientific curiosity. It's a reminder of how much we still have to learn about the universe. It challenges us to refine our tools and techniques, to think creatively about how we observe and interpret the cosmos. And it raises deeper questions about the nature of matter itself. What if the missing baryons aren't just hiding in the WIM? Could they be part of structures or phenomena we haven't yet imagined? Or might they be tied to the elusive nature of dark matter and dark energy, hinting at connections we've yet to uncover? What makes this mystery so compelling is that it's not just about finding missing matter. It's about understanding the universe's intricate web of connections. Every discovery brings us closer to piecing together the cosmic puzzle, but it also reveals new layers of complexity. The missing baryon problem reminds us that even the most familiar aspects of the universe can hold profound surprises, urging us to keep exploring, keep questioning, and keep searching for answers. And as we peer deeper into the cosmos, who knows what other hidden threads we might uncover, weaving together the story of everything that is, was, and ever will be. As we delve deeper into the mysteries of the cosmic microwave background, or CMB, we encounter a peculiar feature that seems to defy one of the most fundamental principles of cosmology, the idea that the universe is uniform in all directions. This principle, known as the cosmological principle, has long been a cornerstone of our understanding of the cosmos. But what if it's not entirely accurate? Enter the axis of evil, an unexpected alignment in the CMB that has left scientists both intrigued and baffled. This mysterious feature suggests that the universe might have a preferred direction, a concept that challenges everything we thought we knew about its structure and origins. First detected in the early 2000s by NASA's Wilkinson Microwave Anisotropy Probe, the axis of evil refers to an unusual pattern in the CMB's temperature fluctuations. Instead of being randomly distributed, these fluctuations appear to align along a specific axis, as if the universe itself has a kind of cosmic tilt. To put it simply, the CMB isn't as uniform as we'd expect. This alignment is so striking that it's been given a name that evokes a sense of cosmic unease, the axis of evil. But what could be causing this strange phenomenon? Is it just a statistical fluke, or does it hint at something more profound? One possibility is that the axis of evil could be the result of an observational bias or an error in how we interpret the data. After all, the CMB is incredibly subtle, and even the smallest miscalculations could lead to misleading conclusions. However, multiple independent studies have confirmed the existence of this alignment, making it harder to dismiss as a simple mistake. Another explanation is that it might be a remnant of the early universe, a kind of cosmic fingerprint left over from the Big Bang. If that's the case, it could offer clues about the universe's initial conditions and the forces that shaped it in its earliest moments. But here's where things get even more intriguing. The axis of evil doesn't just challenge the cosmological principle, it also raises questions about the nature of the universe itself. Could it be evidence of a larger, more complex structure that we're only beginning to understand? Some scientists have speculated that it might be linked to dark energy or even the influence of a parallel universe. While these ideas are still speculative, they highlight just how little we know about the forces that govern the cosmos. The axis of evil isn't just a scientific puzzle, it's a gateway to a deeper understanding of the universe. What makes this alignment so compelling is that it doesn't just challenge our theories, it challenges our very way of thinking about the universe. For centuries, we've assumed that the cosmos is isotropic, the same in all directions. But the axis of evil suggests that there might be a preferred direction, a kind of cosmic north that could reshape our understanding of space and time. It's a humbling reminder that even our most fundamental assumptions can be upended by new discoveries. As scientists continue to study this enigmatic feature, new missions and advanced technologies promise to shed light on its origins. Projects like the European Space Agency's Planck satellite have already provided more detailed maps of the CMB, offering fresh insights into the axis of evil. Yet, despite these advances, the mystery remains unresolved. Each new observation brings us closer to understanding this cosmic anomaly, but it also raises new questions, reminding us just how much we still have to learn. The axis of evil isn't just a scientific curiosity, it's a call to exploration. It invites us to question our assumptions, to rethink our understanding of the universe, and to remain open to the possibility that there's always more to discover. Whether it's a statistical anomaly, a relic of the early universe, or something far more extraordinary, the axis of evil reminds us that the cosmos is full of surprises, waiting for us to uncover them. And as we continue to explore the depths of space, who knows what other cosmic enigmas might be waiting to challenge our understanding of the universe. Stretching across an unimaginable expanse of over 500 million light-years, the Great Wall stands as one of the most colossal structures ever discovered in the universe. This vast filament of galaxies, bound together by gravity, defies our expectations of how the cosmos should look on such a grand scale. It's not just a random scattering of stars and galaxies, it's a cosmic superstructure, a thread in the intricate web that connects the universe's largest building blocks. But what makes the Great Wall so extraordinary isn't just its size, it's the questions it raises about the very nature of the universe itself. At the heart of this mystery lies the cosmological principle, a foundational idea in modern astronomy that assumes the universe is uniform on large scales. In other words, if you zoom out far enough, the cosmos should look roughly the same in every direction. But the Great Wall challenges this assumption. Its sheer scale and density suggest that the universe isn't as uniform as we thought, at least not on the largest scales. How did such a massive structure form? And what does its existence tell us about the forces that shape the cosmos? The answer likely lies in the delicate dance of gravity and dark matter. In the early universe, tiny fluctuations in density ripples left over from the Big Bang set the stage for the formation of cosmic structures. Over billions of years, gravity amplified these ripples, pulling matter together into vast filaments and clusters. The Great Wall is one of the most dramatic examples of this process, a testament to the power of gravity to sculpt the universe on an epic scale. But even this explanation leaves us with questions. Why did this particular filament grow so large, and are there even more massive structures waiting to be discovered? What's fascinating about the Great Wall is that it's not just a static relic of the past, it's a dynamic, evolving structure. Galaxies within the wall are constantly moving, pulled by the gravitational forces of their neighbors. Some are colliding, merging into larger galaxies, while others are being flung outward, carried along the filament like leaves on a cosmic river. This ongoing dance of creation and destruction offers a glimpse into the life cycle of galaxies and the forces that shape them. But the Great Wall isn't just a scientific curiosity. It's a window into the universe's history and future. By studying its structure and composition, astronomers can learn more about how the cosmos evolved from its chaotic beginnings into the relatively orderly universe we see today. It also raises intriguing questions about what lies beyond. If the Great Wall is one of the largest structures we've found, could there be even larger ones waiting to be discovered? And what might they tell us about the limits of the universe's complexity? The discovery of the Great Wall reminds us that the universe is far more intricate and awe-inspiring than we often assume. It challenges us to rethink our understanding of cosmic architecture and to remain open to the possibility that there's always more to discover. Whether it's a product of gravity's relentless pull or a sign of deeper, hidden forces, the Great Wall stands as a monument to the universe's boundless creativity. And as we continue to explore the cosmos, who knows what other extraordinary structures might be waiting to reveal their secrets? Nestled within the vast expanse of the universe lies a region so empty, so eerily desolate, that it might hold the key to one of the most puzzling anomalies in the cosmos. Known as the Eridanus Supervoid, this colossal expanse of nothingness spans an astonishing 1 billion light-years, a staggering distance that's difficult to even fathom. But what makes this supervoid so intriguing isn't just its size. It's the possibility that it might be connected to the enigmatic cold spot in the cosmic microwave background, or CMB. This peculiar region of the CMB, as we've discussed earlier, is significantly colder than its surroundings, and the Eridanus Supervoid might just be the missing piece of the puzzle. So, what exactly is a supervoid? Unlike the dense clusters of galaxies and stars that populate much of the universe, a supervoid is an enormous region where matter is conspicuously absent. It's like a cosmic hole, a vast emptiness that stands in stark contrast to the vibrant web of galaxies surrounding it. The Eridanus Supervoid is one of the largest such voids ever discovered, and its sheer scale challenges our understanding of how cosmic structures form and evolve. But how could something so empty have such a profound effect on the CMB? The answer lies in a phenomenon known as the integrated Sachs-Wolf effect. As light from the CMB travels through the universe, it can gain or lose energy depending on the gravitational fields it encounters. When this light passes through a supervoid, the lack of matter weakens the gravitational pull, allowing the photons to gain a tiny bit of energy. This energy gain shifts the light to slightly longer wavelengths, making it appear colder. If the Eridanus Supervoid is indeed responsible for the cold spot, it would mean that this vast emptiness has left its mark on the very fabric of the universe itself. But the Eridanus Supervoid isn't just a potential explanation for the cold spot, it's also a window into the universe's early history. Some scientists speculate that it could be the remnant of an ancient cosmic event, a kind of scar left over from the universe's tumultuous beginnings. Others suggest that it might simply be a natural part of the universe's structure, a product of the random fluctuations in density that occurred during the Big Bang. Regardless of its origins, the Eridanus Supervoid forces us to confront the fact that even the emptiest regions of space can hold profound significance. What makes this supervoid so fascinating is that it challenges our assumptions about the universe's uniformity. We often think of space as a relatively even distribution of galaxies and stars, but the Eridanus Supervoid reminds us that the cosmos is far more complex and varied than we imagine. Its existence raises questions about the nature of cosmic voids and their role in shaping the universe. Are they simply empty spaces, or do they play an active part in the universe's evolution? And what other secrets might they hold? As astronomers continue to study the Eridanus Supervoid, new observations and simulations are shedding light on its properties and its potential connection to the cold spot. Advanced telescopes and mapping techniques are allowing us to probe deeper into these vast empty regions, offering fresh insights into their structure and impact. Yet, despite these advances, the Eridanus Supervoid remains a mystery, a testament to the fact that even the emptiest parts of the universe are full of surprises. The Eridanus Supervoid isn't just a scientific curiosity. It's a reminder of how much we still have to learn about the cosmos. It invites us to explore the gaps in our knowledge, to question our assumptions, and to remain open to the possibility that even the emptiest spaces can hold profound meaning. Whether it's a relic of the early universe or a natural part of its structure, the Eridanus Supervoid challenges us to think bigger, to look deeper, and to keep searching for answers in the vast, uncharted expanse of the universe. At the heart of our Milky Way, where stars crowd together in a dazzling dance of light and gravity, lies a place of immense power and mystery, the galactic center. Here, amidst the swirling chaos of dust and gas, a supermassive black hole named Sagittarius reigns supreme, its gravity bending space and time to its will. But this cosmic monarch isn't alone. Surrounding it are phenomena so strange, so inexplicable, that they've left scientists puzzled for decades. From mysterious radio signals to bursts of gamma-ray emissions, the galactic center is a hotspot of cosmic anomalies, a place where the ordinary rules of physics seem to break down. What's causing these strange signals, and what do they tell us about the heart of our galaxy? One of the most intriguing mysteries is the source of powerful radio waves emanating from the galactic center. These signals, detected by radio telescopes around the world, don't match the behavior of any known celestial objects. They're erratic, unpredictable, and unlike anything we've observed elsewhere in the universe. Some scientists speculate that they could be coming from dense clouds of gas and dust, energized by the intense gravitational forces near the black hole. Others have proposed more exotic explanations, such as the presence of dark matter particles interacting in ways we don't yet understand. Whatever their origin, these radio waves are a tantalizing clue that there's more going on at the galactic center than meets the eye. Then there are the gamma-ray emissions, bursts of incredibly high-energy radiation that seem to defy explanation. These gamma rays, detected by space-based observatories like NASA's Fermi Gamma-Ray Space Telescope, are among the most energetic phenomena in the universe. One leading theory suggests that they're produced by cosmic rays, high-speed particles accelerated to nearly the speed of light colliding with gas clouds near the black hole. But here's the twist: the gamma-ray emissions don't always align with the expected sources, leaving scientists to wonder if there's another hidden mechanism at work. Could it be the result of exotic physics, or even the activity of an advanced extraterrestrial civilization? While that last idea is highly speculative, it's a reminder of how much we still have to learn about the forces at play in the galactic center. Adding to the intrigue is the discovery of strange, filament-like structures near Sagittarius A. These filaments, stretching for dozens of light-years, emit radio waves in a way that suggests they're being influenced by powerful magnetic fields. Some researchers believe they could be the remnants of past explosions or collisions, while others think they might be part of a larger, unseen structure shaped by the black hole's immense gravity. Whatever their origin, these filaments are a vivid reminder that the galactic center is a dynamic, ever-changing environment, full of surprises waiting to be uncovered. What makes these anomalies so fascinating isn't just their strangeness, it's what they reveal about the complexity of our galaxy. The galactic center is a place of extremes where gravity, radiation, and magnetism collide in ways we're only beginning to understand. It's also a window into the universe's past, offering clues about how galaxies form and evolve over billions of years. By studying these mysterious signals and structures, scientists can piece together the story of our galaxy's birth and growth, shedding light on the forces that shaped it into the cosmic masterpiece we see today. But perhaps the most exciting aspect of the galactic center is what it tells us about the future. As our telescopes and instruments grow more advanced, we're gaining unprecedented access to this enigmatic region, uncovering new details with each observation. Projects like the Event Horizon Telescope, which captured the first ever image of a black hole, are pushing the boundaries of what we thought was possible, revealing the galactic center in ways we've never seen before. Each discovery brings us closer to understanding the mysteries of Sagittarius A and its surroundings, but it also raises new questions, reminding us just how much we still have to explore. The galactic center anomaly is more than just a scientific puzzle, it's a testament to the enduring allure of the unknown. It challenges us to rethink our assumptions, to push the limits of our knowledge, and to remain curious in the face of the universe's deepest secrets. Whether it's the strange radio signals, the bursts of gamma rays, or the enigmatic filaments, each mystery is a piece of a larger puzzle, one that invites us to keep exploring, keep questioning, and keep marveling at the wonders of the cosmos. And as we peer into the heart of our galaxy, who knows what other extraordinary discoveries might be waiting to light up our understanding of the universe. One of the most profound puzzles in modern cosmology lies in a single number, the Hubble constant. This number, which tells us how fast the universe is expanding, might seem like a straightforward piece of data. But here's the catch: depending on how you measure it, you get different answers. This inconsistency, known as the Hubble tension, has become one of the most hotly debated topics in astronomy. It's not just a minor discrepancy. It's a glaring inconsistency that could point to a fundamental flaw in our understanding of the universe. Let's break it down. The Hubble constant is named after Edwin Hubble, the astronomer who first discovered that the universe is expanding. By measuring how fast galaxies are moving away from us, we can calculate the rate of this expansion. But here's where things get tricky. When scientists use the cosmic microwave background, the afterglow of the Big Bang, to measure the Hubble constant, they get one value. But when they use a method called the distance ladder, which involves observing nearby stars and supernova, they get a different, slightly higher value. These two methods, both rigorously tested and widely accepted, shouldn't disagree, but they do, and the gap between them is too big to ignore. So what's causing this tension? One possibility is that there's something wrong with our measurements. Maybe we're misjudging the brightness of certain stars or misinterpreting the data from the CMB. But after years of scrutiny, both methods have held up and the discrepancy remains. This has led some scientists to consider a more radical idea. Perhaps our understanding of the universe itself is incomplete. Could there be new physics at play, an unknown force or particle that's influencing the expansion rate in ways we don't yet understand? It's a tantalizing thought, but one that comes with profound implications. Another angle is that the Hubble tension might be hinting at a deeper mystery about dark energy, the mysterious force driving the universe's accelerated expansion. If dark energy behaves differently than we currently assume, it could explain why our measurements don't align. Alternatively, the tension might be a sign that the universe's expansion isn't as uniform as we think, with different regions expanding at slightly different rates. This idea, while speculative, would challenge the very foundation of the cosmological principle, the assumption that the universe looks the same in all directions. What makes the Hubble tension so compelling is that it's not just a technical problem, it's a gateway to new discoveries. If we can resolve this discrepancy, it could lead to breakthroughs in our understanding of dark energy, the nature of the early universe, and even the laws of physics themselves. It's a reminder that science thrives on questions, not just answers, and that even the most well-established ideas can be upended by new evidence. As astronomers continue to refine their measurements and explore new theories, the Hubble tension remains a beacon of curiosity, urging us to dig deeper and think bigger. Whether it's a flaw in our methods, a sign of new physics, or something entirely unexpected, this cosmic puzzle is a testament to the fact that the universe is always ready to surprise us. And as we strive to solve it, we're not just learning about the expansion of the cosmos, we're expanding the boundaries of our own understanding. Far beyond the icy realm of Neptune, where the sun's light is little more than a faint glimmer, there's a hint of something massive lurking in the shadows. The orbits of several distant Kuiper belt objects, icy remnants left over from the solar system's formation, are behaving in ways that defy explanation. Instead of following the neat, predictable paths we'd expect, these objects seem to be tugged by an unseen force, as if an invisible hand is guiding their movements. This cosmic enigma has led scientists to propose the existence of a hidden giant, a planet so distant and faint that we've yet to catch even a glimpse of it. Welcome to the mystery of Planet 9. The Planet 9 hypothesis began to take shape in 2014, when astronomers noticed something strange about the orbits of a handful of Kuiper belt objects. These objects, some of which are billions of miles from the Sun, share a peculiar alignment. Their orbits are tilted in a similar direction and clustered in a way that suggests they're being influenced by something massive. That something could be a planet roughly 10 times the mass of Earth, orbiting far beyond Neptune. The idea isn't as far-fetched as it might sound. After all, our solar system is no stranger to hidden worlds. Neptune itself was discovered in 1846 because of its gravitational influence on Uranus, proving that planets can be found by their effects on other objects. But here's the twist: finding Planet 9 is no easy task. If it exists, it's incredibly far away, somewhere between 300 and 700 times Earth's distance from the Sun. At that distance, even a planet 10 times Earth's size would be incredibly faint, reflecting only the tiniest fraction of sunlight. To make matters worse, its orbit could take thousands of years to complete, meaning it might not even be in the part of the sky we're currently searching. It's like trying to find a needle in a cosmic haystack, one that's constantly moving. Despite these challenges, the search for Planet 9 has sparked a wave of excitement in the scientific community. Astronomers have turned to some of the most powerful telescopes in the world, like the Subaru telescope in Hawaii, to scan the skies for any sign of this elusive world. They've also used computer simulations to predict where Planet 9 might be hiding, based on the movements of the Kuiper belt objects it's thought to influence. While no definitive evidence has been found yet, the hunt continues, driven by the tantalizing possibility of discovering a new member of our solar system's family. Of course, not everyone is convinced that Planet 9 is the answer. Some scientists argue that the strange orbits of these Kuiper belt objects could be the result of a different, less dramatic explanation. Perhaps a passing star long ago disrupted their paths, leaving them in their current alignment. Or maybe the combined gravitational pull of smaller objects in the Kuiper belt is responsible. These alternative theories highlight the complexity of the problem and remind us that in science, even the most compelling hypotheses need to be rigorously tested. What makes the Planet 9 hypothesis so captivating isn't just the possibility of finding a new planet, it's what it represents about our quest to understand the solar system. It's a reminder that even in our own cosmic backyard, there are still secrets waiting to be uncovered. Whether Planet 9 turns out to be real or not, the search itself is pushing the boundaries of our knowledge, forcing us to rethink what we know about the outer reaches of the solar system. As astronomers continue their hunt, each new observation brings us closer to solving this cosmic puzzle. Projects like the Vera C. Rubin Observatory, set to begin operations in the next few years, promise to revolutionize our ability to detect faint, distant objects. If Planet 9 is out there, it's only a matter of time before we find it. And if it's not, well, the search will lead us to other discoveries, other mysteries, and perhaps even more questions about the vast, uncharted frontier that lies beyond Neptune. After all, the universe is full of surprises, and sometimes the journey to find them is just as exciting as the destination. In the vast cosmic dance, galaxies aren't static islands of stars. They're dynamic, ever-changing entities, often drawn together by the irresistible pull of gravity. This cosmic tango can lead to one of the most dramatic events in the universe, galactic cannibalism, a process where galaxies collide and merge, reshaping themselves and their surroundings in spectacular fashion. It's not just a rare occurrence, it's a fundamental part of how galaxies evolve. And here's the kicker, our own Milky Way is destined to experience this cosmic collision firsthand. In about 4.5 billion years, we'll meet our galactic neighbor, the Andromeda Galaxy, in a merger that will redefine the night sky as we know it. But what exactly happens when galaxies collide, and what does this tell us about the universe's grand design? When galaxies merge, the process is anything but gentle. Imagine two vast collections of stars, gas, and dark matter hurtling toward each other at hundreds of thousands of miles per hour. The gravitational forces at play are immense, creating a chaotic and violent interplay of energy and matter. Stars don't typically collide. Space is too vast, and stars too small relative to the distances between them. But the gas and dust within galaxies do interact, compressing and igniting bursts of star formation in dazzling displays known as starbursts. These regions, glowing with newborn stars, light up the merging galaxies like cosmic fireworks, painting a vivid picture of creation amidst destruction. Over time, the gravitational tug of war between the two galaxies reshapes their structures. Spiral arms stretch and warp, forming intricate bridges and tails of stars and gas that stretch across millions of light years. Eventually, the two galaxies settle into a single, more massive elliptical galaxy, a process that can take billions of years. The result is a galaxy that bears little resemblance to its progenitors, a cosmic phoenix rising from the ashes of its former self. But galactic cannibalism isn't just about destruction, it's also about creation. The mergers of galaxies play a crucial role in the evolution of the universe. They trigger the formation of new stars, seed the growth of supermassive black holes, and contribute to the large-scale structure of the cosmos. Without these collisions, the universe as we know it would look very different. In fact, many of the galaxies we see today, including our own Milky Way, are the products of past mergers. Each one is a cosmic mosaic, a testament to the dynamic and interconnected nature of the universe. The upcoming merger between the Milky Way and Andromeda offers a fascinating glimpse into this process. When these two galaxies collide, the night sky as seen from Earth, or whatever planet might host life in the distant future, will be transformed. Andromeda, currently a faint smudge in our night sky, will grow larger and brighter as it approaches, eventually dominating the view. The two galaxies will pass through each other multiple times, their gravitational interactions creating stunning tidal tails and igniting waves of star formation. Over billions of years, they'll settle into a single elliptical galaxy, often referred to as Milkomeda. The Sun and our solar system will likely survive this cosmic dance, but the view from Earth, or whatever remains of it, will be utterly unrecognizable. What makes galactic cannibalism so captivating is how it reveals the universe's capacity for both chaos and beauty. It's a process that destroys and creates, reshapes and redefines, reminding us that the cosmos is anything but static. These collisions are a testament to the dynamic nature of the universe, a reminder that change is woven into the very fabric of existence. And as we look out at the night sky, we're not just seeing a snapshot of the cosmos, we're witnessing a story of transformation, one that's been unfolding for billions of years and will continue long after we're gone. Galactic cannibalism isn't just a cosmic spectacle, it's a window into the forces that shape the universe. It challenges us to think beyond the familiar, to see the cosmos as a living, evolving entity. And as we continue to study these collisions, we gain a deeper understanding of our place in the grand tapestry of the universe, a tapestry that's constantly being rewoven by the dance of galaxies. Whether it's the eventual merger of the Milky Way and Andromeda or the countless other collisions happening across the cosmos, galactic cannibalism reminds us that the universe is always in motion, always changing, and always full of surprises. Among the most dazzling and mysterious objects in the cosmos are quasars, celestial powerhouses so bright that they outshine entire galaxies. These luminous beacons are fueled by supermassive black holes at their cores, devouring matter at an astonishing rate and releasing unimaginable amounts of energy. But here's the puzzle. Quasars didn't just appear randomly throughout the universe's history. The earliest ones formed incredibly quickly after the Big Bang, lighting up when the universe was less than 1 billion years old. How could such massive, complex structures, supermassive black holes surrounded by swirling disks of gas and dust, emerge so soon after the universe's birth? This is the Quasar Mystery, and it's a question that challenges our understanding of the cosmos's early days. To grasp the scale of this mystery, let's step back for a moment. Quasars aren't just bright, they're unimaginably bright. A single quasar can outshine a galaxy containing hundreds of billions of stars. This incredible energy comes from the supermassive black holes at their centers, which can weigh billions of times more than our Sun. As matter falls into these black holes, it heats up and emits radiation across the electromagnetic spectrum, creating the brilliant glow we observe. But here's the catch: forming a supermassive black hole of that size isn't easy. It takes time, or at least it should. Yet the earliest quasars formed in a cosmic blink of an eye, raising questions about how such massive objects could grow so quickly. One possibility is that the seeds of these supermassive black holes formed in the dense, chaotic environment of the early universe. In those first moments after the Big Bang, tiny fluctuations in density could have created regions of space where matter collapsed into massive clumps. These clumps, in turn, might have grown into the first black holes, rapidly accumulating matter and energy to become the powerhouses we see as quasars. Another theory suggests that the earliest black holes might have formed through the direct collapse of massive gas clouds, bypassing the usual process of star formation altogether. These direct collapse black holes could have grown much faster, providing a possible explanation for the rapid appearance of quasars. But quasars aren't just relics of the past, they're also key players in the story of how galaxies evolve. The intense radiation and powerful winds they produce can influence the growth and structure of their host galaxies, shaping the cosmos on a grand scale. In some cases, quasars might even halt star formation in their galaxies, blowing away the gas and dust needed to create new stars. In others, they might trigger bursts of star formation, acting as cosmic architects that sculpt the universe around them. This interplay between quasars and galaxies is a reminder of how interconnected the cosmos truly is, with even the most distant objects shaping the universe in profound ways. What makes quasars so fascinating isn't just their brightness or their speed of formation, it's what they reveal about the universe's infancy. By studying these ancient beacons, we're catching a glimpse of a time when the cosmos was young, chaotic, and full of potential. Quasars are like cosmic time capsules, preserving clues about the conditions and processes that shaped the universe in its earliest moments. They challenge us to rethink our understanding of black hole formation, galaxy evolution, and even the nature of time itself. As we continue to study quasars with ever more powerful telescopes, each new discovery brings us closer to solving the mystery of their origins. Projects like the James Webb Space Telescope are already peering deeper into the universe's past than ever before, revealing quasars and their host galaxies in unprecedented detail. These observations are helping us piece together the story of how the first black holes formed, how they grew, and how they shaped the cosmos we see today. And as we uncover more about these dazzling objects, we're not just learning about quasars, we're uncovering the secrets of the universe itself. Each quasar is a beacon of light in the cosmic darkness, guiding us toward a deeper understanding of the cosmos and our place within it. Picture this: two incredibly dense remnants of dead stars, each just a dozen miles across but weighing more than our sun, hurtling toward each other at nearly the speed of light. When they collide, the result is nothing short of cosmic fireworks, a burst of energy so intense it sends ripples through the fabric of space-time itself. This isn't science fiction, it's exactly what happened in August 2017, when astronomers detected the collision of two neutron stars for the first time. The event, known as GW 170817, wasn't just a spectacular display of cosmic power, it was a scientific goldmine, quite literally. The collision produced both gravitational waves, ripples in space-time predicted by Einstein's theory of general relativity, and a dazzling flash of light across the electromagnetic spectrum. This dual signal, dubbed a multi-messenger event, marked a turning point in astronomy, allowing scientists to study the same phenomenon in two completely different ways. The gravitational waves detected by the LIGO and Virgo observatories provided a precise measurement of the event's location and energy. Meanwhile, telescopes around the world captured the light emitted by the collision, revealing a kilonova, a brief but brilliant explosion that confirmed long-held theories about the origins of some of the universe's heaviest elements. Among the most exciting discoveries was the confirmation that neutron star collisions are cosmic forges for elements like gold, platinum, and uranium. These heavy elements, known as R-process elements, are thought to form in the extreme conditions created during such collisions. As the two neutron stars merged, they ejected a cloud of neutron-rich material into space. This material rapidly underwent a process called rapid neutron capture, or the R process, forming heavy elements in a matter of seconds. The light from the kilonova revealed the unmistakable signatures of these elements, solving a mystery that had puzzled scientists for decades. Where does all the gold in the universe come from? The answer, it turns out, lies in the explosive deaths of neutron stars. But the significance of this collision goes far beyond glittering metals. Neutron-star mergers are natural laboratories for studying some of the most extreme physics in the universe. The densities and temperatures involved are so extreme that they mimic conditions found nowhere else, not even in the cores of supernova. These events allow scientists to test theories about the behavior of matter under conditions that are impossible to recreate on Earth. For example, the collision provided insights into the equation of state of neutron stars, a description of how matter behaves at such incredible densities. This information is crucial for understanding the nature of these mysterious objects and the limits of how much matter can be compressed before it collapses into a black hole. What's more, neutron star collisions offer a unique opportunity to study the expansion of the universe. By comparing the distance measured by gravitational waves with the redshift of the light from the kilonova, scientists can refine their estimates of the Hubble constant, the rate at which the universe is expanding. This approach, known as the standard siren method, provides an independent way to measure cosmic distances, helping to resolve the ongoing tension between different measurements of the Hubble constant. The collision of two neutron stars is more than just a fleeting cosmic event. It's a window into the universe's most fundamental processes. It's a reminder that even the most violent and chaotic events in the cosmos can lead to creation, forging the very elements that make up our world and our bodies. As we continue to observe and study these collisions, each new discovery brings us closer to understanding the forces that shape the universe, and who knows? The next neutron star collision might reveal even more secrets, offering fresh insights into the nature of space, time, and the building blocks of everything we know. Imagine the universe not as a random scattering of stars and galaxies, but as a vast, intricate tapestry, a cosmic web woven from threads of dark matter and gas, connecting galaxies across unfathomable distances. This web isn't just a metaphor, it's the hidden scaffolding of the cosmos, a structure so immense that it shapes everything we see. Galaxies aren't isolated islands floating in empty space. They're nodes in this colossal network, linked by filaments of invisible dark matter and glowing gas. But how does this cosmic web form, and what does it tell us about the universe's grand design? The story of the cosmic web begins in the earliest moments of the universe, just after the Big Bang. Tiny fluctuations in density ripples in the fabric of space-time set the stage for the web's creation. Over billions of years, gravity amplified these ripples, pulling matter into dense clusters and leaving behind vast, empty voids. The result is a network of filaments that connect galaxies like beads on a string, with dark matter acting as the invisible threads that hold it all together. This structure isn't static, it's a dynamic, ever-evolving framework that continues to shape the universe around us. One of the most fascinating aspects of the cosmic web is its role in galaxy formation. Galaxies don't just form anywhere, they are born in the densest regions of the web where filaments intersect. These intersections act as cosmic crossroads, funneling gas and dust into swirling clouds that eventually collapse to form stars and galaxies. The web's filaments act like cosmic highways, guiding the flow of matter and energy across the universe. Without this structure, galaxies might never have formed in the way we see them today. It's a reminder that the universe isn't just a collection of objects, it's a system, interconnected and interdependent. But the cosmic web isn't just a map of where galaxies are, it's also a map of where they're going. As galaxies move through the web, they're pulled by the gravitational forces of the filaments and clusters around them. This movement isn't random, it follows the web's intricate patterns, creating flows of galaxies that ripple across the cosmos. By studying these flows, astronomers can trace the history of the universe's expansion and even predict its future. The cosmic web is like a time machine, offering glimpses into the universe's past and its ultimate fate. What makes the cosmic web so extraordinary is its scale. The largest filaments stretch for hundreds of millions of light years, connecting galaxy clusters that themselves contain thousands of galaxies. These filaments are so vast that they challenge our understanding of how such structures can form and persist. Yet, despite their size, they're incredibly delicate threads of gas and dark matter that are easily disrupted by the forces around them. It's a paradox that lies at the heart of the cosmic web, a structure both immense and fragile, shaping the universe while remaining hidden from view. Scientists are only beginning to unravel the secrets of the cosmic web. Advanced telescopes and computer simulations are allowing us to map its structure in unprecedented detail, revealing patterns and connections that were once invisible. Projects like the Sloan Digital Sky Survey have created stunning three-dimensional maps of the web, showing how galaxies are distributed across the cosmos. Meanwhile, simulations of the early universe are helping us understand how the web formed and how it continues to evolve. Each new discovery brings us closer to understanding the universe's hidden architecture, but it also raises new questions about the forces that shape it. The cosmic web isn't just a scientific curiosity, it's a reminder of how much we still have to learn about the universe. It challenges us to think bigger, to see the cosmos not as a collection of isolated objects but as a connected whole. It's a testament to the power of gravity, the influence of dark matter, and the intricate dance of matter and energy that shapes everything we see. And as we continue to explore this vast, invisible network, who knows what other secrets we might uncover. The cosmic web is more than a map of the universe, it's a story, one that's still being written, one thread at a time. As we peel back the layers of the cosmos, we arrive at one of the most mind-bending ideas in modern science, the multiverse theory. This concept suggests that our universe, the one we see, filled with stars, galaxies, and planets, might not be the only one. Instead, it could be just one of countless universes, each with its own unique set of physical laws, constants, and even dimensions. Picture an infinite tapestry of realities where the rules of physics as we know them might not apply. In some universes, gravity could be stronger or weaker. In others, light might travel at a different speed or matter might behave in ways we can't even imagine. It's a staggering thought, one that challenges everything we think we know about existence. The multiverse theory didn't emerge out of thin air. It's rooted in some of the most cutting-edge areas of physics, including quantum mechanics and string theory. For instance, quantum mechanics tells us that particles can exist in multiple states at once, until they're observed. Some interpretations of this phenomenon suggest that every possible outcome of a quantum event actually happens, but in separate, branching universes. Meanwhile, string theory, which attempts to unify all the forces of nature, proposes the existence of higher dimensions where other universes could reside. These theories, while speculative, provide a framework for imagining a multiverse, a cosmic landscape far richer and more complex than we've ever imagined. But why should we care about the multiverse? One of the most compelling reasons is that it offers a potential solution to one of the deepest mysteries in science, the fine-tuning of our universe. The fundamental constants of nature, like the strength of gravity or the mass of an electron, are perfectly calibrated to allow for the existence of stars, planets, and life itself. If any of these values were even slightly different, the universe as we know it wouldn't exist. This precision has led some to wonder, is it just a cosmic coincidence or is there a deeper explanation? The multiverse theory suggests an answer. If there are infinite universes, each with different physical laws, it's inevitable that at least one of them would have the right conditions for life. In this view, our universe isn't special, it's just one of countless possibilities. Of course, the multiverse theory isn't without its skeptics. Some argue that it's untestable since by definition, other universes would be beyond our reach. How can we prove the existence of something we can't observe? Others worry that it risks becoming a catch-all explanation, a way to sidestep difficult questions without providing concrete answers. These are valid concerns, and they highlight the challenges of exploring such an abstract idea. Yet, even as a speculative concept, the multiverse pushes the boundaries of our imagination, forcing us to confront questions about the nature of reality itself. What makes the multiverse theory so captivating isn't just the science, it's what it says about our place in the cosmos. If there are indeed other universes, each with its own history, laws, and maybe even life, it changes how we think about our own existence. Are we just one possibility among an infinite array of realities? Or is there something uniquely significant about our universe, even in the face of such vast diversity? These questions don't just belong to physicists, they're deeply human, touching on our curiosity, our creativity, and our desire to understand the world around us. The multiverse theory reminds us that the universe or universes are far stranger and more wondrous than we can imagine. It's a concept that invites us to dream bigger, to explore the limits of our knowledge, and to embrace the mysteries that lie beyond our current understanding. Even if we never prove the existence of other universes, the journey of asking these questions enriches our view of the cosmos and our place within it. And as we continue to push the boundaries of science, who knows what other extraordinary ideas might emerge, challenging us to rethink the very fabric of reality. Now, let's step into one of the most mind-bending concepts in physics, a phenomenon that feels like it's straight out of science fiction, but is very much a part of our reality. Welcome to the world of time dilation, a cornerstone of Einstein's theory of relativity. At its core, time dilation reveals that time isn't the constant, unchanging force we often assume it to be. Instead, it's fluid, stretching and compressing depending on gravity and velocity. This isn't just a theoretical idea. It's been proven time and time again, from the precision of GPS satellites to experiments with atomic clocks. But what does it mean for us, and how does it reshape our understanding of the cosmos? Imagine two identical clocks, one placed on Earth and the other launched into space aboard a high-speed spacecraft. According to Einstein's theory, the clock in space, moving faster and experiencing weaker gravity, would tick slightly slower than the one on Earth. This might sound like a small difference, but over time it adds up. In fact, astronauts aboard the International Space Station, orbiting at speeds of about 17,500 miles per hour, age slightly slower than people on the ground. Over the course of a 6-month mission, the difference is mere milliseconds, but it's a real, measurable effect that confirms Einstein's predictions. But time dilation isn't just a quirk of space travel, it's a fundamental feature of the universe. Near massive objects like black holes, where gravity is incredibly intense, time slows down dramatically. If you could hover near the edge of a black hole and watch a clock fall in, you'd see its hands slow to a crawl as it approached the event horizon. For the clock, time would pass normally, but from your perspective, it would appear almost frozen. This extreme example highlights just how deeply gravity and motion are woven into the fabric of time itself. It's a reminder that time isn't a universal constant. It's a dynamic, flexible dimension shaped by the forces around us. The implications of time dilation are staggering, especially when we think about the future of space exploration. As we venture deeper into the cosmos, the effects of traveling at near light speeds could become more pronounced. For astronauts on a mission to a distant star, time might pass more slowly for them than for those left behind on Earth. A journey that takes decades for the travelers could span centuries or even millennia for those waiting at home. This raises fascinating questions about the nature of human exploration and the challenges we'll face as we push the boundaries of what's possible. Could time dilation one day allow us to reach distant worlds within a single lifetime, or will it create a rift between travelers and the societies they leave behind? Beyond its practical implications, time dilation challenges us to rethink our most basic assumptions about reality. If time can stretch and bend, what does that mean for the nature of existence itself? Is time truly linear, or is it a more complex, multi-dimensional construct? These questions don't just belong to physicists, they invite all of us to ponder the mysteries of the universe and our place within it. Time dilation reminds us that even the most familiar aspects of our lives, like the ticking of a clock, are part of a much larger, more intricate cosmic dance. As we continue to explore the universe, time dilation will remain a key piece of the puzzle, shaping our understanding of space, time, and the forces that bind them together. It's a phenomenon that bridges the gap between the theoretical and the tangible, offering a glimpse into the profound interconnectedness of the cosmos. And while it may challenge our intuition, it also opens the door to new possibilities, pushing us to imagine a universe far stranger and more wondrous than we've ever dreamed. So the next time you glance at a clock, take a moment to consider, time isn't just passing, it's bending, stretching, and weaving the story of the universe itself. Deep within the vast expanse of space, invisible particles hurtle through the cosmos at nearly the speed of light, carrying with them energies that defy comprehension. These are cosmic rays, high-energy particles that bombard Earth from all directions, yet their origins remain one of the most enduring mysteries in astrophysics. While we know some cosmic rays come from supernova, the explosive deaths of massive stars, others appear to have sources far more exotic and elusive. What could be powerful enough to accelerate these particles to such incredible speeds? And what do they reveal about the universe's most energetic phenomena? Cosmic rays aren't rays in the traditional sense. They're actually particles, mostly protons, but also heavier atomic nuclei and even electrons. When they collide with Earth's atmosphere, they create cascades of secondary particles, a phenomenon that has been studied for over a century. Yet, despite decades of research, pinpointing their exact sources has proven to be a formidable challenge. Supernova are a likely culprit for some of these particles, as the shock waves from these colossal explosions can accelerate particles to extreme energies. But here's the twist: the highest energy cosmic rays can't be explained by supernova alone. Their energies are so immense that they must come from something far more powerful. This is where things get truly fascinating. Some of the most energetic cosmic rays may originate from the most extreme objects in the universe, black holes and neutron stars. Near a black hole's event horizon, the intense gravitational forces and magnetic fields can act like cosmic particle accelerators, boosting particles to velocities approaching the speed of light. Similarly, neutron stars, with their crushing densities and unimaginably strong magnetic fields, could also serve as cosmic ray factories. These objects are nature's ultimate powerhouses, capable of generating energies that dwarf anything we could ever produce on Earth. But the mystery doesn't end there. One of the most puzzling aspects of cosmic rays is their directionality, or lack thereof. Unlike light, which travels in straight lines, cosmic rays are charged particles, meaning they're deflected by magnetic fields as they journey through space. By the time they reach Earth, their original paths are scrambled, making it nearly impossible to trace them back to their sources. This has led scientists to develop ingenious methods for studying these particles, from ground-based detectors to space observatories, all in an effort to unravel their origins. The study of cosmic rays isn't just an academic pursuit. It's a window into the universe's most extreme environments. These particles carry clues about the processes that shape the cosmos, from the violent deaths of stars to the mysterious workings of black holes and neutron stars. They also provide a unique opportunity to test the limits of our understanding of physics. For instance, the highest energy cosmic rays challenge our models of particle acceleration, pushing us to rethink how energy is transferred in the universe. Could there be entirely new mechanisms at play, or even undiscovered cosmic phenomena driving these particles to such incredible speeds? What makes cosmic rays so captivating is their ability to connect us to the universe's most energetic events, even if we can't see them directly. They're a reminder that the cosmos is a dynamic, ever-changing place, filled with forces and phenomena that stretch the boundaries of our imagination. As we continue to study these enigmatic particles, each new discovery brings us closer to understanding the universe's most powerful accelerators and the secrets they hold. Whether they come from supernova, black holes, or something even more extraordinary, cosmic rays are a testament to the universe's boundless energy and the endless mysteries waiting to be uncovered. Beyond our solar system, a universe of worlds awaits, thousands of them, each with its own unique story. Since the first exoplanet was discovered in the early 1990s, astronomers have uncovered a staggering diversity of planets orbiting distant stars. These aren't just variations on the familiar worlds we know. They're entirely new categories of planets, from scorching hot Jupiters to massive super-Earths, each challenging our understanding of how planetary systems form and evolve. What makes these discoveries so extraordinary isn't just the sheer number of exoplanets we've found. It's how they're reshaping our view of the cosmos and our place within it. Take hot Jupiters, for example. These gas giants, similar in size to Jupiter but orbiting perilously close to their stars, were among the first exoplanets discovered, and they completely upended our expectations. How could a planet so massive form so close to its star, where temperatures are hot enough to melt metal? The answer lies in the chaotic dance of planetary migration, where gravitational interactions can send planets spiraling inward, transforming their orbits and creating environments unlike anything in our solar system. These fiery worlds are a reminder that planetary systems can be far more dynamic and unpredictable than we once thought. Then there are super-Earths, rocky planets larger than our own but smaller than gas giants. These worlds, which don't exist in our solar system, are some of the most common exoplanets we've found. But what exactly are they like? Are they rocky deserts, waterlogged worlds, or something entirely different? The answer depends on their composition, atmosphere, and distance from their star. Some super-Earths might be covered in vast oceans, while others could have thick, toxic atmospheres that make them utterly inhospitable. Each discovery adds a new piece to the puzzle, helping us understand the incredible range of conditions that can exist on other planets. But perhaps the most tantalizing exoplanets are those that lie within their star's habitable zone, the so-called Goldilocks zone, where temperatures might allow liquid water to exist. Finding such worlds is a critical step in the search for life beyond Earth. Already, we've identified several candidates like Proxima Centauri b, a rocky planet orbiting the closest star to our Sun. While we don't yet know if these planets are truly Earth-like, they offer hope that somewhere out there, another world might harbor the conditions needed for life. The challenge now is to study their atmospheres, looking for signs of oxygen, water vapor, or other biomarkers that could hint at the presence of life. What makes exoplanet research so exciting is that it's not just about finding new worlds, it's about understanding the processes that shape them. Every exoplanet discovery teaches us something new about planetary formation, from the role of stellar winds to the influence of neighboring planets. It's a field that's constantly evolving, driven by new technologies like the James Webb Space Telescope, which is already revealing the atmospheres of distant worlds in unprecedented detail. With each new observation, we're piecing together a more complete picture of the universe's planetary diversity. Exoplanets are more than just scientific curiosities. They're a testament to the boundless creativity of the cosmos. They remind us that the universe is far more varied and dynamic than we ever imagined, filled with worlds that stretch the limits of our imagination. And as we continue to explore these distant planets, we're not just learning about the universe, we're learning about ourselves and the possibilities that lie beyond our own blue planet. Whether it's a scorching hot Jupiter, a mysterious super-Earth, or a potentially habitable world, each exoplanet discovery brings us one step closer to answering one of humanity's oldest questions: are we alone in the universe? The search is far from over, but with every new world we find, the cosmos feels a little less vast and a little more full of promise. Hidden within the swirling arms of galaxies, there's an invisible force at work, one that doesn't emit light or cast shadows, yet shapes the cosmos in profound ways. These are galactic magnetic fields, vast networks of magnetic energy that stretch across millions of light years, weaving through the fabric of space itself. While we can't see them directly, their influence is undeniable, guiding the birth of stars, steering the paths of cosmic rays, and even shaping the evolution of galaxies. But how do these magnetic fields form, and what secrets do they hold about the universe's grand design? Galactic magnetic fields are thought to originate from the chaotic motions of charged particles within galaxies. As stars form and die, they release streams of charged particles into the surrounding space. These particles, influenced by the galaxy's rotation and the turbulent motions of gas and dust, generate electric currents. Over time, these currents give rise to magnetic fields, a process known as the dynamo effect. It's a bit like stirring a pot of soup. The motion creates swirls and eddies, and in galaxies, those swirls become magnetic fields. But here's the twist: these fields aren't static. They're dynamic, evolving structures that can grow, twist, and even reverse direction over millions of years. One of the most fascinating roles of galactic magnetic fields is their influence on star formation. Stars are born in dense clouds of gas and dust, and magnetic fields play a crucial role in shaping these clouds. They can either help or hinder the process depending on their strength and orientation. In some cases, magnetic fields provide support against gravity, preventing clouds from collapsing too quickly. In others, they channel gas into dense filaments, creating the perfect conditions for stars to ignite. This delicate balance between magnetic forces and gravity is a key factor in determining how and where stars form, making these invisible fields essential architects of the cosmos. But magnetic fields don't just shape stars, they also guide the journey of cosmic rays, high-energy particles that zip through space at nearly the speed of light. As cosmic rays travel through a galaxy, they interact with its magnetic fields, spiraling along the field lines like beads on a wire. This interaction not only affects the paths of cosmic rays, but also influences how they spread throughout the universe. Without galactic magnetic fields, cosmic rays might travel in straight lines, making their origins easier to trace. Instead, their winding paths make them one of the most elusive phenomena in astrophysics, a reminder of how deeply magnetic fields are woven into the cosmic tapestry. Despite their importance, galactic magnetic fields remain one of the least understood aspects of the universe. Measuring them is no easy task, as they don't emit light or other forms of radiation we can easily detect. Instead, scientists rely on indirect methods, such as observing the polarization of light from distant stars or the behavior of cosmic rays. These observations have revealed that magnetic fields are not uniform. They vary in strength and direction across a galaxy, creating a complex and dynamic landscape. This complexity makes them both a challenge and an opportunity for astronomers, offering a window into the processes that shape galaxies over billions of years. What makes galactic magnetic fields so captivating is how they connect the smallest scales of the universe to the largest. From the birth of individual stars to the evolution of entire galaxies, these invisible forces play a role in nearly every cosmic process. They're a reminder that the universe is more than just stars and planets. It's a web of interconnected forces, each influencing the other in ways we're only beginning to understand. And as we continue to study these magnetic fields, each new discovery brings us closer to unraveling the mysteries of the cosmos. The study of galactic magnetic fields isn't just about understanding the universe, it's about understanding ourselves. These fields are part of the story of how stars, planets, and ultimately life came to be. They're a testament to the intricate and delicate balance of forces that make the universe what it is. And as we peer deeper into the cosmos, we're reminded that even the most invisible forces can have the most profound impact, shaping the universe in ways that are as beautiful as they are mysterious. So, the next time you look up at the night sky, remember, there's more to the cosmos than meets the eye. There's an invisible web of magnetic energy, quietly shaping the story of the universe itself. Imagine a particle so elusive that it can pass through an entire planet without so much as a whisper of interaction. A ghostly traveler that defies detection yet holds the key to understanding some of the universe's most powerful events. These are neutrinos, nearly massless particles that flood the cosmos, produced in staggering numbers by stars, supernova, and even the Big Bang itself. Despite their abundance, neutrinos are famously difficult to study. They rarely interact with matter, slipping through Earth and even our bodies by the trillions every second without a trace. Yet, their very elusiveness makes them invaluable messengers, carrying secrets from the heart of supernova, the cores of stars, and the earliest moments of the universe. Neutrinos are born in some of the most extreme environments in the cosmos. When a massive star explodes in a supernova, for instance, it releases an unimaginable burst of energy and with it a flood of neutrinos. These particles escape the collapsing star long before light does, offering scientists a kind of cosmic early warning system. In fact, when supernova 1987 exploded in the Large Magellanic Cloud, neutrino detectors on Earth picked up a burst of these particles hours before the light from the explosion reached us. It was a groundbreaking moment, marking the first time neutrinos had been detected from a supernova and proving their potential as cosmic messengers. But supernovae aren't the only sources of neutrinos. The Sun, our closest star, is a prolific neutrino factory. Every second, billions of these particles stream out from the Sun's core, where nuclear fusion transforms hydrogen into helium. Detecting these solar neutrinos has helped scientists confirm our understanding of how stars work, but it's also revealed something puzzling. For decades, we detected fewer solar neutrinos than our models predicted. This discrepancy, known as the solar neutrino problem, led to a startling discovery: neutrinos can change their identity or flavor as they travel. This phenomenon, called neutrino oscillation, proved that neutrinos have mass, albeit an incredibly tiny one, and opened up new questions about their role in the universe. What makes neutrinos so fascinating isn't just their ability to change flavors, it's what they can tell us about the universe's most energetic processes. Because they interact so weakly with matter, neutrinos can travel vast distances without being absorbed or scattered, carrying information from their point of origin directly to us. This makes them ideal probes for studying environments that are otherwise inaccessible, like the dense cores of stars or the chaotic aftermath of a supernova. They're like cosmic spies sneaking out of the most extreme places in the universe to deliver their secrets. Yet, detecting neutrinos is no simple task. To catch these ghostly particles, scientists have built massive detectors deep underground, shielded from the noise of cosmic rays and other interference. One of the most famous is the Ice Cube Neutrino Observatory in Antarctica, which uses a cubic kilometer of ice as a detector. When a neutrino occasionally interacts with the ice, it produces a faint flash of light which sensors can pick up. These rare interactions are like whispers in the dark, offering fleeting glimpses into the lives of these enigmatic particles. The study of neutrinos is more than just an exercise in particle physics, it's a journey into the heart of the cosmos. These particles connect us to the most violent and energetic events in the universe, from the deaths of stars to the birth of galaxies. They challenge our understanding of matter, energy, and the fundamental laws of physics, pushing us to rethink what we know about the universe. And as we continue to refine our detectors and expand our knowledge, each new neutrino detected brings us closer to unlocking the mysteries of the cosmos. Neutrinos remind us that even the smallest, most elusive particles can have an outsized impact on our understanding of the universe. They're a testament to the power of curiosity and innovation, showing that with the right tools and persistence, we can uncover the secrets of the cosmos one ghostly particle at a time. When we think of space, we often imagine it as a smooth, empty expanse, a quiet stage where the drama of the cosmos unfolds. But what if, when we zoom in close enough, that serene stage turns into a bubbling, chaotic sea? This is the mind-bending concept of quantum foam, a theoretical idea that suggests space-time itself is anything but smooth at the tiniest scales. Instead, it's a frothy, churning landscape where the very fabric of reality fluctuates wildly, constantly bubbling with energy and potential. It's a place where the rules of classical physics break down, and the quantum world takes center stage, revealing a universe far stranger and more dynamic than we ever imagined. The idea of quantum foam arises from the marriage of quantum mechanics and general relativity, two pillars of modern physics that don't always play nicely together. Quantum mechanics describes the behavior of particles at the smallest scales, where uncertainty reigns and particles can pop in and out of existence. General relativity, on the other hand, paints space-time as a smooth, continuous fabric warped by gravity. But when we try to apply both theories to the tiniest scales, think distances a trillion times smaller than an atom, the result is a chaotic, unpredictable froth. Space-time itself becomes a seething soup of tiny fluctuations, with particles and energy appearing and disappearing in a frenzy of quantum activity. So, what does this quantum foam actually look like? Imagine a turbulent ocean where waves and bubbles constantly rise and fall, collide and merge. Now shrink that ocean down to an unimaginably small scale and replace the water with space-time itself. At this level, the very fabric of the universe is no longer smooth or static. It's a dynamic, ever-changing foam with tiny bubbles of space-time constantly forming and dissolving. These fluctuations are so small and fleeting that they're impossible to observe directly, yet their existence is a key prediction of quantum gravity, a theoretical framework that seeks to unify quantum mechanics and general relativity. But why should we care about something so abstract and seemingly untouchable? Quantum foam isn't just a theoretical curiosity, it has profound implications for our understanding of reality. For one, it challenges the idea that space and time are fundamental, unchanging entities. Instead, it suggests that they're emergent phenomena arising from the chaotic interactions of the quantum world. This idea flips our perspective on its head, forcing us to rethink the very nature of existence. Are space and time just illusions emerging from a deeper, more fundamental layer of reality? The quantum foam hypothesis opens the door to such questions, inviting us to explore the universe at its most fundamental level. One of the most exciting aspects of quantum foam is its connection to black holes and the birth of the universe itself. Some theories suggest that the intense gravitational fields near black holes could amplify the effects of quantum foam, creating regions where space-time is so distorted that it becomes unrecognizable. Similarly, in the earliest moments of the Big Bang, the universe was so small and dense that quantum foam would have dominated, shaping the initial conditions from which everything we see today emerged. These connections make quantum foam not just a theoretical playground for physicists, but a key piece of the puzzle in understanding the universe's origins and evolution. Of course, the idea of quantum foam isn't without its challenges, because it operates at scales far beyond our current ability to observe or measure. It remains a theoretical construct, a tantalizing possibility rather than a proven fact. Yet, it's precisely this mystery that makes it so compelling. Quantum foam pushes the boundaries of our knowledge, forcing us to confront the limits of our understanding and to imagine a universe far more complex and dynamic than we've ever dreamed. It's a reminder that even the most fundamental aspects of reality, space and time, are still full of surprises waiting for us to uncover them. As we continue to explore the quantum realm, each new discovery brings us closer to understanding the true nature of space-time. Whether quantum foam is ultimately confirmed or replaced by a new theory, its existence challenges us to think bigger, to question our assumptions, and to remain curious about the universe's deepest mysteries. After all, the cosmos isn't just a collection of stars and galaxies, it's a living, breathing tapestry, woven from threads of energy, matter, and the ever-shifting fabric of space-time itself. And in that tapestry, even the smallest threads hold the key to understanding the grandest designs of the universe. Picture this, a universe that began with a bang, expanding and evolving over billions of years, filled with galaxies, stars, and planets. But like all great stories, it must come to an end, or does it? The ultimate fate of the cosmos is one of the most profound mysteries in science. Will it collapse back in on itself in a fiery big crunch? Will it stretch into an eternal frozen void? Or will it meet some other, even more enigmatic destiny? The answer lies in the delicate balance between the forces that shape the universe, forces like dark energy, gravity, and the relentless expansion of space itself. One of the leading theories about the universe's end is the Big Freeze, also known as heat death. In this scenario, the universe continues to expand at an accelerating rate driven by dark energy. Over trillions of years, galaxies will drift farther and farther apart until they're so distant that their light can no longer reach one another. Stars will burn out and new ones will cease to form, leaving the cosmos cold, dark, and empty. It's a chilling vision of the future where entropy, the measure of disorder, reaches its maximum, and the universe fades into a lifeless, eternal silence. But the Big Freeze isn't the only possibility. Another idea is the Big Crunch, a dramatic reversal of the universe's expansion. If dark energy weakens over time, gravity could eventually take over, pulling everything back together in a cataclysmic collapse. Galaxies, stars, and even atoms would be crushed into an unimaginably dense point, perhaps triggering a new Big Bang and restarting the cycle of creation. This cyclical model of the universe offers a poetic symmetry where endings are also beginnings, and the cosmos is reborn from its own ashes. Then there's the Big Rip, a more violent and chaotic scenario. If dark energy grows stronger over time, it could tear the fabric of space itself apart. Galaxies, stars, and even planets would be ripped to shreds, followed by atoms and subatomic particles. In this scenario, the universe doesn't just fade away, it's torn apart in a final, violent act. It's a stark reminder of the power of dark energy and the delicate balance that governs the cosmos. The question of how the universe will end isn't just a scientific curiosity. It's deeply tied to the nature of dark energy, the mysterious force driving the universe's accelerated expansion. Understanding dark energy is one of the greatest challenges in modern cosmology, and it holds the key to predicting the universe's ultimate fate. Is dark energy constant, or does it change over time? The answer could determine whether we're headed for a big freeze, a big crunch, or something entirely unexpected. What's fascinating about these theories is that they're not just abstract ideas, they're windows into the fundamental forces that shape the universe. They challenge us to think beyond our own lifetimes, even beyond the lifespan of stars and galaxies, and to consider the grandest scales of time and space. They remind us that the universe is dynamic, ever-changing, and full of surprises, even in its final act. As we continue to explore the cosmos, each new discovery brings us closer to understanding its ultimate fate. Advanced telescopes like the James Webb Space Telescope are peering deeper into the universe than ever before, revealing clues about dark energy and the expansion rate of the cosmos. These observations are helping us refine our models and predictions, but they're also raising new questions. Will the universe end with a whisper, a bang, or something we haven't even imagined yet? The story of the universe's end is still being written, and we're just beginning to uncover its final chapters. It's a humbling reminder of how much we still have to learn, and how the cosmos continues to surprise us at every turn. Whether the universe meets a quiet, frozen end or a dramatic, fiery collapse, one thing is certain. Its story is far from over, and the journey to uncover its secrets is as thrilling as the destination itself. So, as we gaze at the stars and ponder the future, let's remember that the universe's greatest mysteries are still waiting to be solved, and that the answers might be closer than we think. For decades, humanity has gazed at the stars, wondering if we're truly alone in the vast expanse of the cosmos. This question has driven one of the most ambitious scientific endeavors of our time, the search for extraterrestrial intelligence, or SETI. Since its inception in the 1960s, SETI has aimed to answer one of humanity's oldest and most profound questions: are we the only intelligent life in the universe? By scanning the skies for signals that could indicate the presence of alien civilizations, SETI represents our best effort to reach out across the void and find someone or something out there. Yet, despite decades of searching, the silence remains unbroken. Why is that? Are we alone, or are we simply not listening in the right way? The core idea behind SETI is straightforward. If intelligent civilizations exist elsewhere, they might be using technology that emits detectable signals such as radio waves or laser beams. These signals, even if unintentional, could serve as a cosmic beacon announcing their presence to the universe. To capture these potential messages, SETI programs use some of the most advanced radio telescopes in the world, like the Allen Telescope Array in California, to listen for patterns that stand out against the background noise of space. The challenge, of course, is separating potential alien signals from the countless natural and human-made sources of interference, from pulsars to satellite transmissions. But here's the twist: the universe is unimaginably vast, and the signals we're searching for might be incredibly faint or fleeting. Imagine trying to pick up a single whisper in a roaring stadium. That's the scale of the challenge SETI faces. To make matters more complex, alien civilizations might be using communication methods we haven't even imagined yet. What if they're transmitting in ways that don't involve radio waves or lasers? What if their technology is so advanced that it's beyond our current ability to detect? These questions highlight the immense difficulty of the search and remind us that our efforts are limited by our own understanding of physics and technology. One of the most compelling aspects of SETI is how it forces us to confront our assumptions about life and intelligence. We often assume that extraterrestrial civilizations would be similar to us, using technology, communicating in ways we can recognize, and perhaps even sharing our curiosity about the universe. But what if they're not? What if their forms of intelligence are so different from ours that we wouldn't even recognize them as life? This idea, known as the alienness problem, challenges us to think beyond our own experiences and consider the infinite possibilities that might exist in the cosmos. Despite the lack of definitive results, SETI has made significant strides in refining its methods and expanding its reach. Projects like Breakthrough Listen, funded by billionaire Yuri Milner, are bringing new resources and technology to the search, scanning millions of stars and galaxies for signs of intelligent life. Meanwhile, advancements in artificial intelligence are helping to sift through the massive amounts of data generated by these observations, increasing the chances of spotting a signal that might otherwise go unnoticed. These efforts are a testament to humanity's persistence and ingenuity as we continue to push the boundaries of what's possible in our quest to find others. What's perhaps most inspiring about SETI is not just the search itself, but what it says about us. It's a reflection of our curiosity, our desire to connect, and our willingness to imagine a universe that's larger and more wondrous than we can fully comprehend. Even if we never find conclusive evidence of extraterrestrial intelligence, the journey of searching expands our understanding of the cosmos and our place within it. It reminds us that the universe is full of mysteries waiting to be uncovered, and that the act of seeking is as important as the answers we hope to find. So, as we continue to scan the skies and listen for whispers from the stars, let's remember that the search for extraterrestrial intelligence is about more than just finding aliens. It's about exploring the unknown, challenging our assumptions, and embracing the boundless possibilities of the universe. Whether we're alone or not, the stars will always hold secrets, and the quest to uncover them will continue to inspire us for generations to come. As we reach the end of this cosmic journey, one thing is abundantly clear. The universe is a treasure trove of mysteries, each one a testament to the breathtaking complexity and wonder of existence. From the enigmatic wow signal to the elusive dark matter, from the haunting silence of the Fermi Paradox to the dazzling brilliance of quasars, these 32 compelling pieces of evidence remind us just how much we have yet to uncover. Every discovery, every anomaly, every unanswered question is a reminder that the cosmos is far stranger and more intricate than we could ever imagine. What makes these mysteries so captivating isn't just their scientific significance, it's the way they challenge us to think bigger, to dream beyond the boundaries of our current knowledge. They invite us to question what we know, to explore what we don't, and to remain open to the possibility that the universe is always ready to surprise us. Whether it's the hidden forces shaping galaxies or the fleeting whispers of cosmic rays, each mystery is a piece of a larger puzzle, one that we're only beginning to piece together. As we continue to probe the depths of space, who knows what answers we'll uncover? Perhaps we'll find evidence of life beyond Earth or unravel the true nature of dark energy. Maybe we'll discover entirely new phenomena that defy our current understanding of physics. Whatever lies ahead, one thing is certain: the journey of exploration is far from over. With every new telescope, every groundbreaking mission, and every innovative theory, we're inching closer to unlocking the secrets of the cosmos. But this journey isn't just for scientists, it's for all of us. Each of us plays a part in this grand adventure, whether it's by sharing our curiosity, supporting scientific endeavors, or simply looking up at the night sky with a sense of wonder. The universe belongs to everyone, and its mysteries are ours to explore together. So, as we close this chapter, let's keep the conversation going. What do you think lies beyond the next cosmic horizon? Which of these mysteries fascinates you the most? Share your thoughts in the comments below, and let's keep exploring the cosmos together. Don't forget to like, subscribe, and join us as we dive deeper into the wonders of the universe. The stars are calling, and the journey is just